Okay, so good. So now we have Obed Santos from CBPF. Yeah, please go ahead.
Thank you so much. Thank you, first of all, as I would say, thank you for Carlos for the invitation. It was definitely a pleasure to be here, close by to my region, Northeast, and a very nice place, warm water on the beach. So I hope that you guys have enjoying or have a good time. So, as I say, my name is Obed Santos. Now I'm part of the CBPF, which is in Portuguese Centro Brasileiro de Pesquisas Físicas, which stands for, in English, for Brazil Center for Research in Physics. In fact, this institute is the institute directly, which directly follow or organized by the Ministry of Science Technology. So we are a research physics institute with a master's, with a PhD, and of course a lot of research. Is very old. Was founded in '49. Back then days, our motto is that where there's physics, there is CBPF. So CBPF involves all different kinds of physics, since I don't know, cosmology, gamma ray detectors, condensed matter physics, and everything. Biophysics as well, and all these sorts of physics. So as I say, so since March this year, so I got a permanent position over there. So that means that I'm established or pushing for start a research group in specifically magnonics, nanofabrication, and magnetism as well, and a few other things to the material and of all sorts of nanoscopic, mesoscopic physics related. So for those that are not familiar with, CBPF is located in Rio de Janeiro, which is roughly about 2,000, more than 2,000 kilometers from here, from Natal. For those that not picturize what Rio de Janeiro it is, this is a photo of Rio de Janeiro. Okay, everything. Well, that picture works a lot if I'm outside of Brazil, but we are here in Natal, which also have very nice places to go as well. So as you can see, this is like a postcard photo. It is a postcard photo, but is also a photo or an image that we can see our research institute, which is right here in that corner. So that building here is our institute, so it's well located, let's say. So as I say, is quite old for Brazilian standards. We have like all very famous people that founded the CBPF. For example, Cesar Latz, which got 7 indications for Nobel Prize, didn't get, but got a lot of indications for the discovery of meson pi. We have the first publication was done by Elisa Frota Pessoa back to 1950s. And we also have like a very famous people that have given some classes, performed some experiments back in CBPF. One of most famous ones is this guy. This guy, Feynman, has been in Brazil for performing some experiments, some lectures between 50 and 52. He's right here in that corner here. He's Cesar Lattes. Leite Lopes, who also founded of CBPF back that time. And of course, he came to do science, but as well, he came to enjoy the carnival. So as everyone knows how famous, and gambling, correct, indeed. We have like a very famous casino back there in Urca, close by, so he was there a lot as well. So, but before that, I have been in University of Cambridge working Professor Chiara Sicarelli, and back then I have been in University of Groningen working directly in magnon devices, working with Professor Bart van Wies. So because the topic is quantum magnonics, or as we have discussed here, quantum-ish magnonics, or quantum-to-be magnonics, that means that I will try to highlight a few results, or the things that I would like to discuss involve some results back the time that I were working with Professor Bart van Wies. So that's it will highlight. But it's also part of the driving force, or one of the backbones of the research that I want to develop in CBPF. So I would like also in advance give some acknowledgements for the ones that help to perform those experiments that I would like to discuss today. So I'll try to very briefly I'll mention a few things that might be important. I believe that everyone are aware of those effects, but you never know. So it's sometimes it's nice to confirm that. So one of the things, one of the primo things that we have to discuss is the spin current. So if you have like if you think about charge current, you can picturize as electrons with the opposite spins move in the same direction. So if you count the numbers of charge that is transport, you have a charge current. But if you count the numbers of spins, spin up, spin down, they are cancelled. So you don't have, let's say, a flow of spins, flow of angular momentum, the famous H bar that we all talking about. But if you do, for some reason, has two electrons or one electrons that moving with different spin moving different directions, in that case, you do have a net spin current, or in that case, a pure, what we call pure spin current, but the amount of charge current that is delivered is zero. So, so this is one of the definition of the spin current that you can think about. And every time that you talk about spin currents or spintronics, that means that you have somehow to look for the magnetism or the magnetism from that system. Not necessarily magnetism, can be some kind of isolate spins, but somehow some kind of coherent entanglement between the spins somehow. So frequently in spintronics and also magnonics, you look to the magnetization, think about the movements of spins, or the other way around. So the both fields are a little bit entangled. So, and one of the primo things as well, because the spin is sometimes can be slightly complicated to measure, one of the major effects that we use frequently in our experiments is the spin to charge conversion or charge to spin conversion. So let's say that you have a charge current passing through material with a high spin optical coupling. You get a deviation from these movements in a perpendicular direction and end up with a spin current. So if you think about that, if let's say that you have a platinum, you apply a charge current, so you create a spin current through the thickness of the platinum, which end up with spin accumulation at the top and the bottom of the interfaces. So this is what is important. So you accumulate spins, so you accumulate angular momentum that for some reason can be, or some ways can be transferred for your magnetization or your different materials and situations. But one of the things that important, of course, obey the Onsager's reciprocity, so the other way is true. So if you somehow have a spin current inject into this material, you can produce a voltage. And that's the tricky and the nice thing that I think about this field. You end up with a voltage that's completely or directly proportional to the spin current. So this is one of the beauties of for my opinion, for this field. But the thing is,
so Diakonov would not be happy with this previous slide.
Ooh, nice. Good to know. Good to know.
Because of the reference, right? You know, Hirsch basically reinvented his
Correct.
stuff back in the 70s.
Yeah. Yeah, of course, because the Diakonov also performed these experiments or proposed this conversion effect back to 1972. So if I'm not forgetting about. But okay, sorry about that. But continuing. So in this picture that I show, you understand that you can transport spin current by the movement of these free electrons or free polarized electrons. But in the same way or similar way, we can transport the angular momentum, this spin current, via the collective spin wave spin current. So that means that instead of free electrons moving around, we have a collective motion of the magnetization that deliver the similar or proportional angular momentum to one side to another. So if you're talking about spin waves, that means that you can rewrite the things in terms of magnus, because magnus is the quantization of the spin waves, or the quantum quasi-particle that describe the spin wave motion of magnetic material. So you can think about a ground state, everyone is pointing up, but the first excited state is not exactly flipping one spins, but take this angular momentum to deviate through the thickness or the length of your lattices. But I think things was discussed here before, so we are quite know that magnets can travel long distance. How long can be? We have this discussion with Bill. Well, as I say, a few microns maybe, or centimeters can be. If you do some kind of correction, I don't know, meters, kilometers? No, I don't think so, but okay. But you can also use magnons to interchange electronic signals. This is another very interesting thing that we can do it. It is one of the things that we did it. We try to explore. So the other thing is that in some way you can describe the whole dynamics of magnetic material or one of the magnetic materials in terms of magnons. For example, you could say that the ferromagnetic resonance that stands for every magnetic or spin of the magnetization procession the same way, same coherent way, is a magnon with a k equal to 0 with wavelength of infinity. And this usually, as we discussed before, is in the range of gigahertz, which corresponds to these coherent magnons, which sometimes is settled or defined by the geometry of your environment or magnetic material or structure. But on top of this, if you think about a single flip of your magnetization in a site, you can think about this is an extremely high frequency magnon, very localized magnon that sometimes do not exactly behaves of coherent thing, but behaves as diffusion system. So magnons that you increase the magnonic chemical potential that behaves as diffusive system, as Professor So pointed out yesterday. So that means that at the end of my talk, I will try to bring back this, let's say, ranges of magnons, or how can you somehow correlate those range of different devices that behaves using coherent magnons, and devices that behaves, or which is important to understand, the diffusive behaviors of those magnons. So this is a little bit my outline. As I say, a brief introduction. Then I'll try to discuss a little bit about the transport of magnons. Well, Professor So did an amazing job yesterday, so it's very useful for today. Then I move, or what I call cavity magnonics. I will say that's not exactly cavity magnonics, but indeed, I somehow I create a cavity magnonic, or try to build up a cavity magnonic in some way. And finally, some outlooks. I think is this conference, this workshop is a very nice place to think about ahead, or think about outside the box, or I don't know. So that's I think I will try to do it. So one of the major motivations for the transport of magnons, back to the data DAS spin transistor, where you have like a source, a collector, and the flow of polarized spin current, or polarized, or simply spin or spin current somehow. In this case, to the electron gas, that you transport information somehow. So the idea is to try to do some similar thing using YIG, so using magnons in this case. So we have a injector here, where you apply a charge current, create a spin accumulation at the interface. This accumulation provoke or increase the numbers of magnons in that region, with diffuses, and the reciprocal effect happen here, and you collect back this spin current, measure a voltage. So that's one way that we call no local magnon transport experiments. So this is one picture of our device. Here we can also add a third layer in the middle, in between, to act as a gate, effectively as a transistor for magnons that also point out yesterday. You can also use permalloy in this case. Or, well, the things is it can be as more complicated or complex as possible. So as was pointed out yesterday, this is the basic concept. So you have a spin accumulation at the interface. This spin accumulation creates a magnon by absorption of this angular momentum from this free electron, creating a magnon in that system, diffuses, and in the detector, the opposite thing happens. So you absorb a magnon, polarize a spin, and this creates the spin current on your detector. So as I say, Professor Sohr yesterday made a very nice description, and you will see that the difference between the theoretician and the experimentalist. So in my case, one way to picturize that is that skip stones. So you can think about an electron that you provoke spin waves or magnons into the system, but in the detector the opposite happens, and you back and collect back to this spin and the reciprocal effect happen. So well, that is a way more clever way to describe that, but I like this way. So as I say, this is what exactly happened here, or try to describe here. So this is the mechanism. So as I say, you can treat as diffusion system, increasing the magnon chemical potential. In this case, if you do the experiment, you can rotate your sample and you see a signature of the magnon transport, which are cosine square of your results. If you can also change the magnetic field and you see this behavior. But one of the things important here is that with this experiment, you can also not only demonstrate that you can do transport or intermediate electronic signals via magnons, but you also can study the magnon behavior that is happening here, because this voltage can be proportional, or it is proportional somehow by the conductivity or the conductivity of magnons in your material. So this is one way that you can extract or obtain more information than that. So, and this is what we do. How we do it? We take a film of YEG, perform a series of lithography process, doing the platinum strips, then the collectors, and so on and so forth. And we end up, sometimes you have some problems, right? It's clean room, so dust everywhere. But at the end, you get a very nice device. So one of the questions that we are trying to think about is the thing: what happens if you decrease the thickness of YEG? Because somehow you could think that in that case, the YEG is the wire where the magnons or electrons are flowing. So the question is exactly what happens if you decrease the thickness of the YEG. So one of the results that we got was somehow surprising, because if you take like let's say 200 nanometers YEG, with this dashed line is right here. So if you decrease the thickness of YEG, in fact your no local voltage increases. So this was slightly surprising, because well, you have less YEG, let's say, to flow these magnons, but in fact your no local voltage is increasing. So then you can try to compute that, and this is what we get. So for very thick films, and when I say thick, I'm saying above 1 micrometer, we have like a plateau for no local voltage. This seems small, close to 0, but it's not 0, it's measurable. But when you decrease the thickness, this guy goes up very quickly. This was a little bit confusing in the beginning. We tried to explain that using the equations that define or try to compute this no local voltage in terms of the conductivity, spin diffusion length, the factors of conversions of spin to magnons at the interface. And when you compute that with parameters that is reasonable, we find that the conductivity of magnons in the YEG, very thin YEG films, should be quite high. And when I say high, we calculate about a few orders of magnitude. So this was a little bit confusing, and to confirm that, what we did what we tried to do some simulations in COMSOL to finite modeling using the diffusion system. So, and we have like the films or the device, every black dot here is a specific device. And you try to compute to see what the parameters of this magnon conductivity that match with the experimental setup. And when we do this, we do for all the thickness that we have, all the data that we have, we end up with some conductivity of magnons that increases a few orders of magnitudes, which corroborate with this calculation for very close devices. So, and exactly what is happening here, we are there is a few open questions maybe in this system, but what we think that is happening is that we believe that we have a transition of conductivity that goes, let's say, from 3D regime to this 2D conductivity magnons, where somehow you have a constraint of allowed modes that happens in a YEG. So when you decrease below 1 micrometer, you did this constraint of subbands of magnons or channels in your magnons that are allowed decreases, change the way of this conductivity. So as I say, there is a few open questions and a few more things to do. It involves, of course, the research that I want to perform here back to Brazil. So as I say, so in the limit of the things, when you use a very thin YEG film, and I don't know if you pay attention, but the thinnest film was 5.9 nanometers, so this corresponds to a few layers of YEG. So in fact, what we end up with some kind of 2D magnon gas in that system with a high conductivity that can be open for or can be used for further investigation or effectively as a magnetic material or a system that is similar as possible can be from this case, or the magnetic material case for this experiment. The other thing is, can we control the magnons? Yes, we can control these magnons. I'll try to speed up a little bit because Professor So showed a very nice results yesterday about this control, and that we will also have done. So as I say, you can put a third layer in between, and if you apply a DC current, you can rise the numbers of magnons in between the channel or create a depletion of the numbers. And when you do so, you see a feature, your feature of no local resistance increases or decreasing depending the current that you apply in your system. So effectively acting as a transistor, or magnon transistor. So this happens if in platinum, if you have platinum, but if you have permalloy, the things get slightly more complicated. Yeah?
Yeah, so can you go back one?
Sure.
Slide. So I just want to understand the analogy better with I'm familiar with the spin FET.
Okay.
So when you have this third leg there,
Yeah.
the gate, what are you actually controlling? In the original proposal of data and as you're basically controlling the spin orbit interaction, so you control the pitch.
Correct.
Of this spin, texture. What about here? And what is the current that you're saying you're varying? What is the equivalent of the ferromagnets? That they have two currents, right? Instead of So what is blocking or non-blocking
Yeah,
something?
no, that's a very good question. There is no blocking or not blocking. What we do it here is that you externally you are modulating magnetic conductivity. So you can rewrite your magnetic conductivity in your channel that for a term that is the conductivity of the of the YIG itself, plus a term that is thermal, let's say, effects, plus a term that rise or decrease via the current that you apply. So you increase the numbers of magnons in between the channel, which reaching more.
So in this
advanced.
sense, it's like the usual transistor.
Yes.
Right. Okay.
Yes.
The three-legged thing.
Exactly.
Okay, great.
Exactly. But this is a very good question, anyways. But as I say, if you use permalloy as a modulator, why permalloy? Because permalloy also have this spin to charge conversion, and on top of this, he also have a magnon dependent spin to charge conversion. So in fact, we end up not only with the term of the spin Hall effect, but also with the term of a normal spin Hall effect. On top of this, the simple fact of that you have a permalloy on top of the YIG, you have exchange interaction between them that can modulate this non-local resistance depending of the orientation between the YIG film and the permalloy film. So I could stay, let's say, a little bit longer in this results, but I invite you to take a look for these papers. I would like to move a little bit further for distinguish results. But but you can believe in me as well. So if you apply low magnetic field, the permalloy will stay aligned to the strip because of the shape and isotropy. But if the magnetization is sufficient high, you rotate your magnetization of the permalloy that can understood or a higher or lower magnon controlling of the gate by this anomalous spin Hall effect term. So if you are not fully convinced, please take a look for our paper in details. But so this gives me for the second part, let's say, of the talk, that is, instead of now transport magnons through long distance, as we discussed somehow, will be a little bit more involved to control magnons, so confine magnons some regions, some specific places or structures. So the motivation for that is back to one of the most classical system that we do when we start in physics with a potential wall. Well, so if you have a potential well, you have modes inside this potential that are allowed. But so what could be the equivalent in magnons for that? So one way that we can think about, or what we try to work on, is you have what I can call hybrid system, or a YIG film with permalloy, or two sides of permalloy in each side. So that means that now this permalloy will interact or modify the magnet characteristics of the YIG underneath, and somehow you end up with three different regions where the magnets can behave slightly different. So if the magnets behave slightly different, they can somehow bounce back between these regions and and obtain some modes inside this region. This is not exactly something that come up from my mind from nowhere. No, people have also worked on that. They have these very nice experiments where have a permalloy film or cobalt iron bottom, I think, in this case. They also perform with the permalloy, but here is the major result is cobalt iron bottom. So they put a strip of cobalt iron bottom here in the right middle, two antennas each side, excite spin waves to these systems, and what they find out that you can see a dip in this this transport of magnon spin wave transport that corresponds of the width of this the width of this strip. Maybe I was a little bit too fast, but now just for disclaimer, now we are talking about exciting coherent magnons. So let's say magnons with 1 gigahertz range. So in this experiment, they apply microwave field in this direction and measure in this one. So using a VNA system. Okay. So so back to our system. In our case, it was slightly different. Instead of having a permalloy or a magnetic material in between, we have the opposite. We have the free YIG in this region. The question is, how can we now measure this guy? Because in the previous experiment, they measure simply between the transport of magnons between two antennas, so a VNA-like experiment. In our case, we tried slightly different. We put a platinum strip right on the center of this cavity, or what we can call constriction or YIG film, and measure the voltage of this as caused by the spin pumping effect. So now what we can do, what we did it was we set a frequency, fixed frequency of 8 gigahertz. So we take this sample, put it on top of strip line, we set the frequency to 8 gigahertz, sweep the magnetic field, and when you measure here, right here in this platinum strip right on the center, we see multiple peaks instead of a single one. So just to confirm these results, this is the classical FMR, or the FMR for the book. Sorry, as I say, we put the sample here on top of a strip line. We excite a fixed magnetic microwave field or microwave current in this strip line and sweep the magnetic field. Classical FMR broadband. So if you do measure the FMR absorption of this YIG film, we end up with a single peak, which corresponds to absorption of this YIG film. Why single in this case of YIG? Because we are talking of 100 nanometers YIG, so the modes are how to say, spin wave modes or not exactly there. So we went up with classical FMR measurements. So then, if I measure the voltage right here in this region, or this platinum strip that we call remote one, that is out of this restriction, what we end up is with a single peak. So if I change the frequency, I change the position in field of this peak. So basically the FMR and spin pump figures are the same. They look the same, but they are different experiments. In one case, you see the absorption of the microwave from the YIG film. The other one, you look in the voltage right here in this device. So the coherence between, or the connection between these two experiments is the fact that now, during the FMR process, you are ejecting spins into the platinum that is converted into a voltage. But basically, you have a probe, which is effectively is that feature, or this image means, is that we can use spin pump voltage as a local probe for coherent excitations of magnon excitations. But again, if I measure here, right here in this constriction device, change the frequency, you see multiple peaks. So this, the black one, is the remote one, while this bluish one is the one inside the cavity. So we see multiple peaks in this guy right here, right here. They have a dispersion relation slightly different from the remote strip, from the book, let's say FMR, but the peaks is right there. So as I say, the spin pump, in this case, the spin pump voltage is probing that we have multiple resonance modes inside this cavity, or this is what they're saying. Yeah?
Or you start making an analogy with the particle in a box and resonances.
Okay.
Can you go back
Sure.
to that slide? I want to understand, do you actually have a barrier or a well in this sense when you have this extra layer there? And the resonances that you're seeing as a function of magnetic field, can you understand them in terms of the usual Fabio-Perot type resonances?
Oh, that's a good question. I don't have, let's say, enough measurements or more, let's say, experiments or calculations for that to be sure if you are talking exactly a box or I don't know, Fabio-Perot like. What I think is happening is more like a Fabio-Perot thing because we can somehow calculate at the end we calculate this behaves as a lossy cavity. So magnons can flow in between this region a little bit. In both cases, not exactly a poop box, like sharp box, but we also have some kind of partial magnons flowing into and back to this case. Yeah? Oh. Okay, have another one.
But I mean, it's easy enough to calculate. You know the dispersion for YIG very well, right? So
Yeah.
you can look which kind of modes would have wavelengths that fit your size there and what. And also, I mean, if you were to change the direction of the magnetic field, you might see
Correct.
some changes there.
Yeah. So that's a very good question. In our setup, we were not able, back that time, we were not able to rotate the system, but yeah, this is in fact we would able to see this change in the features. But indeed what we did it was try to calculate or a very simple model, which is simply assume that we have a box of YIG. So if you have a box of YIG, as Axel point out, you can calculate where these modes can be appears. So we calculate that with simple spin wave theory, that's pretty much. And the modes that now, because you have a sizable YIG film, now you allowed some modes to be to happen. And if you do this calculation, we did this calculation for the parameters of we use the stars right here is the modes, which it's some agreement. So if you go back here, these stars are these modes. So in some parts describe okay, but sometimes not. Of course, because that system is not exactly a finite box. It's a little bit more complex than that, because we have a permaloid outside, not a sharp end of the YIG, but somehow behaves a similar way.
So you're looking at these parts there. Which final numbers are you actually? Because the L is much larger than W, right?
Yeah. So if you go back here, so the width of this is around 2 micrometers. The length 30.
So can you tell us what the numbers are there for this part for the dots?
Oh, that's a very good question. So this is the first mode, second mode, and so on and so forth of this cavity. But of course, as I say, that there's more things that be done. We can do simulation or try to do simulation to be more precise in these modes. But this is the one of the major things that I would like to show up to discuss is that we can now use this voltage as a probe in this kind of material. We can do a slightly more analysis. We can see so these lines corresponds these peaks modes or where this resonance is happening inside the cavity. The black dot is the remote strips that follows the Kittel equation nicely. So if now we plot the spin pumping voltage minus the resonance of the bulk of the YIG, we end up with this kind of cross feature. That's not exactly anti-crossing of these modes, but well, we see maybe that a few modes that coincide with or aligns with the bulk resonance seems to be slightly more intense. So it seems like that we have like a kind of feedback system of the resonance of the YEG film outside and the modes inside this cavity. We did it a little bit more. We try to change the width of this cavity, so increase or decrease. So if you increase or decrease this, the size of the cavity, you allow more or less modes to appear. So more or less this is what will happen. If you decrease the width of this guy, the distance between the peaks seems to be a little bit more spaced. If you increase a little bit more, modes can be allowed or can fit into that things. So this is very reproducible in some sense. This is two different cavities, or let's say resonance cavities that designed to have the same dimension, and they did it coincide the mode. So if you look here, we have the remote strip here for different frequencies. Cavity 1 with, in this case, was 1.6 micrometers. And we have the modes, 6, 7. So cavity C as well, same dimension, and the peaks appears in the same position. Just to make sure this is measurements was performed at the same time. We confirm a little bit more things. One of the things was we replaced the permalloy strip to gold one, just to see if it was like, I don't know, some microwave features, and it's not. So if you replace the gold, the platinum permalloy, sorry, for gold, you see a single peak that is no magnetic material or interaction happened there. So indeed, this cavity or modes arise by this magnetic interaction between the permalloy and the YEG. And and this guy, this is what we call side platinum strip. So this was the voltage right here in this one that don't just have permalloy, let's say, square in one side. But in this case as well, we don't see any multiple features, just a single peak. So with these results, we can try to compute some kind of finesse for this cavity. So in this case, we call some kind of magnonic finesse will be the spacing between the peaks divided by the line width of these peaks. If we do that, we end up with a finesse of around 10, which corresponds to some reflectance, as you point out, at the boundaries around 73%. So this was a little bit higher, well, a few times higher than the previous results in the opposite way. Instead of confined YEG between two permalloy regions, the other results shows the part covered permalloy through two YEG sides films. And this, what happened that we got these results and seems interesting results is because now these modes happens in a pristine YEG. So a YEG without additional losses, let's say, caused by the proximity of the permalloy or further interferences. As I say, this finesse we can try, we calculate or compute this finesse by different frequencies seems to be slightly constant. The average peak space, as I say, increases with frequency as well. So, and if you calculate the finesse and the average peak distance for the difference of width, you end up with this behavior, which indeed increase the peak spacing, increase the finesse if you constrain your region, right? Yeah, you have a microphone?
Hi. The stars are just the magnon modes, right?
Yeah, the spin wave calculation, spin wave theory.
I was wondering about the first peak, because it seems to me that if the magnon modes, if you shift the stars a little bit, everything would like match perfectly, or at least as better than
yeah, that's a very good question. That's a very good question. So if you, and this is one nice thing about this workshop, we can discuss the thing. So, and you can look here. So for low frequencies, this is like let's say, the most appears for lower magnetic field region, while for high frequencies it appears to be slightly off. So that's why I try to show in this case, because you have the cross between these modes and the resonance of the Yeg film, which should be aligned. So what we happen here, or one of the things that we compute, is because of the permalloy in both sides here, permalloy squares, you have anisotropy or effectively magnetic field, or in this. So basically, the Yeg film right here in the center feels also the magnetization of the permalloy. So the effective field is slightly higher. So that's why for low frequencies appears in the fields before the main resonance of the Yeg. And why exactly did deviates for high frequencies, this guy? For high frequencies, that's an open question. I don't know exactly. But because of that, because there is more than just a simple box happen in this case. We have a box, we have interaction, exchange reaction, dipolar interactions happens that was not computed in this stars calculation. Okay. But, oh yeah. Yeah.
Yeah. So, do you have an idea on how the magnetization is distributed along the material as you like do this measurement? Because, okay, you can have it is ferromagnetic, but maybe because of the interactions between permalloy and the you might have some, I don't know, different dipolar interactions in the regions.
Yeah, that's
between.
again, this is a very good question. I have to say this is an open question.
Okay.
We don't have exactly this answer right here. But back to what more or less we're talking about. When you do this calculation, you end up with an isotropy term of 10 we have to add up a little bit this 10 millitesla anisotropy that probably is caused by the proximity with the permalloy squares. So which end up with giving a little bit more effective field in this case. But okay, this is the part of the results set. So now we have some kind of cavity. So, and now somehow I can try to do these connections between these two devices or magnonic devices in that case, because end up of everything we are talking about magnons, or right. So if, as I say, in one system was magnons that behaves as diffusive systems, maybe more in the terahertz region, high frequency magnons localized that diffuses into the system. But in this case, we have confinement coherent magnons that are defined by your geometry. So in this, because it's defined by geometry, this end up for the title of my talk that I will try to explore, all-on-chip magnonic engineering. So why we want to explore the all-on-chip? Because everything is all-on-chip. My phone is all-on-chip. Your computer is all-on-chip. So my credit card is all-on-chip in some sense. So that's me. And why engineering? Because now we can try to play with this interaction or hybridization modes between different systems to perform different structures that we can try to do it. And this is what I want to do it in my new position. So instead of using a permalloy square or a cavity, we can do it a round cavity or a coupled cavity. So instead of two spheres of Yeg, that's macro spins, we can try to build a all-on-chip way or all-on-chip fashion. We can have some coupled cavities where they are connected, and the exchange term between the cavities will be the length of this distance or these cavities. Or I don't know, take a NV center or defect, put on top of this, and analysis how the spin wave corresponds or distribute in these systems. Quantum or make the magnons, the terahertz magnons, flow through a constriction and other things. Maybe try to implement this all-on-chip magnon qubit architecture. I don't know. This is what I think the point that I will try to do it. And the good thing is that also people want to do or think in the some way. So for example, this paper will give a very nice overview of this, showing different, let's say, experiments that together will able to do PCB or make a PCB for magnons, where you have different components, magnonic components that perform or can be could compute or do magnon computing in this case. So this is one very nice overlook of that. That will be end up, as I say, PCB for magnons. That's what we are aiming for. So the other thing is quantum magnonics. Well, quantum magnonics can be anywhere here, or quantum effects could be involved in many places. Could be classical, could be quantum. Doesn't matter. If you at least reach the functionality that we want to, that's a very nice thing to do it. Could be quantum, could be entangled with I don't know, as I say, NV centers or different kind of spin dependent materials or interfaces. 2D material as well can be incorporated to these features. So as I say in the beginning, because I'm try to establish a research group, that means that I need you, I need you somehow, and to try to bring you to collaborate, or students, or any kind of research that you want to perform. I have to show up a few things that we have. We have TEM, we have all the systems for lithography, electron beam lithography. We have a clean room, laser writer, so do many different nanofabrication systems. Sputtering deposition, we have a few ones. Dynacool with possibility for transport measurements, so on and so forth. Now we are setting up this new experiment for NV Center. I have to talk about the Lab Nano on CBPF with open multi-user laboratory for nanofabrication. You can apply your project and we can discuss and try to do some collaboration with that. We also recently we end up getting a Blue Force for studies in qubit. So this setup, or these experiments are being we are setting up this guy and to perform qubits information, quantum information in that systems. This is for the experimentalists. For the theoreticians, no worries. We have a nice place to go. No worries, we have everything. And for the experimental setups, experimentalists as well, if everything works fine, we can set up the experiments here in the morning, have a lunch here, and cross the fingers and go back to collect the data. So far, this did not happen. I stay all the time in the lab, but I could do it. But for the theoreticians, that's perfect place to write a final draft for a paper. So and I went up talking, mentioned about some people. This is the people that have been in CBPF already, that is more related, let's say, to the magnetism. We have Pato Passos Guimarães, Luiz Sampaio, Flávio Garcia, Rubens Sommen, Eduardo Bittar, some names that maybe Brazilians more familiar, but I think you guys as well from outside Brazil, you know. But the people that you might know is the ones that are starting now in the CBPF. We have a huge call, more than 30 position was open, and we filled up. I am one of those, but we have more people, more extremely nice and important people coming. We have André Gadelia, which has amazing, I don't know how many nature cover he has, but he's a very nice guy working with 2D materials. We have Nicolas Prestes, who is amazing in skyrmions. Roberta Trutra, which is a witch on nanofabrication. Carmen Gilardoni was also have a deep understanding in excitons and NV centers, and we have a very nice theoreticians that are joining now in our group, and we are happy to, as I say, on behalf of the CBPF, present it to open for further collaborations. And with that, I think I finished my talk. Thank you so much.
Very much for this
Thank you.
great talk. So please, questions.
Thanks for the talk. I would like to go back to the magnon transport
Sure.
part. So the part in which you say the conductivity increases when the thickness of
Yeah.
of your film is smaller. Actually, I don't know if I understood correctly, but you were saying that you were going to the limit.
Yeah.
So it sounds to me a bit if I understood correctly, you were saying that you have more modes when you were going to this limit, and that's why the conductivity is increasing?
No, not necessary, but well, as I say, there is a few things that we have to improve on this understanding for these results. What you can think about is that numbers of modes that exists in a thicker YEG film is large. So if you could end up with transitions between these modes that not end up giving more magnons
contributing to the
to
conductivity.
that. So when you decrease the thickness, you decrease the numbers of these modes. So this exchange between the modes do not happen anymore, and you have some kind of I don't know, more channels or few channels with high conductivity between this injector detector. This is a little bit more what we are thinking that's happening in this case.
Okay, thanks.
Just to confirm, you're not considering, are you considering dipole-dipole interactions as well in your model to get the energies?
To the cavity one, you mean?
The one that was before this one. So this is only exchange, right? The energy, or do you have other interaction as well in your Hamiltonian to get these energies for your magnons?
No, in this case, is more exchange because we are considering k square. So the simply a parabolic dispersion realization of the mode.
And
So not necessarily the.
And so you are considering different modes along the thickness,
Yeah.
right? What is the thickness compared to the size of your samples? Like the T ig, what is the thickness that you?
Oh, the thickness. Well, the thickness of your materials is like from, I don't know, 5.9 nanometers up to dozens of microns. This is a full range of devices that we have working on. So, but if you compute this energy, you will see that the numbers of occupation decreases a lot. Modes inside the system decreases a lot. So
All right, thank you very much for the interesting talk. So in the magnon transistor device, I think, one of the earlier slides, you had this case where you had transport modulated by changing the magnetic, this one. I didn't quite catch the physical mechanism for why the transport is modulated here. I didn't.
Yeah, I think I did not mention indeed, but that is another one. But what we're also thinking what's happening here is that you are allowed more magnons flow or spins flow into your magnet permalloy layer or less, depending of the orientation. Some
sort of like SMR type thing.
Yes.
So it's just like
yeah.
I see.
So and this is not dependent of the current. it this happens without any further input. So basically, for example, I was a little bit fast, but you can see from here. So for large magnetic fields, you are in this case, so where your magnetization is point, the field is here. So the magnetization is point in this case. But when you rotate or go for low magnetic field range, your magnetization of the permalloy points towards the strip, and you end up collecting more voltage in these guys. So this is this feature is currentless features that goes on top of the current dependent modulation. Yeah, I think it's working.
So with the cavity, now you mentioned the reflectivity and whatever. Now, it's reflectivity of what? Because, I mean, if you think about optical cavity, right, we send light and then it gets reflected. What is it here? So is it like if you would send magnets and they would be propagating magnets?
That's a very good question indeed. So if you think about this experiment, this is easy because you have magnets flowing from one side to another. In this case, is that in my head? What is that you have modes inside of the cavity that are trapped, so not coming into this place, but are inside of this region that are excited. And these reflectance could be something. Think about how much magnets can flow out of this region and flow back. And that's, again, this is a very good question because the resonance, right? The resonance of the yake that's just under the permalloy is also modified. So.
And is it correlated with the line widths? Because that would be the mechanism for energy dissipation. So that would increase the line widths.
You mean
you have these confined magnets, right? Now, if it's a cavity, you would expect, okay, that there is some dissipation. There are some dissipation mechanisms which are usual, probably phonons. I don't know what they decay into. But then, if they can also get out of the cavity, that increases the line widths. And I was wondering whether there is any. I mean, of course, you cannot, open and close the mirrors.
Sure.
But maybe you see some evidence in your experiments that it's happening.
What we can see, or if you go to the details, we measure a thicker line width of these modes in comparison, let's say, to pristine yake film. I don't know exactly if you're but we were not able to extract more information from this line width changes in this. But if you I don't think that So if you look this red one, this is what is the analysis of this average peak line width. So, and it in fact decreases with if you have more concentrated features.
Yeah. Okay, so I suggest that we stop here and thank you.
Thank you.
Yeah, so this is one of those hours that we have to discuss, to do whatever, and then we'll go for lunch at 12:30. And in the afternoon, we will have more talks at around 4. But before the coffee break, we also have discussions, and one of the guys is Fabrizio is going to present some very basic stuff on magnets, mostly for students.